exercise 1.1 index laws. So let's start off by taking a look at the number 8. So here I have number 8, and that's a standard form. I can rewrite that as being 2 times 2 times 2, which I can place in index form. So I have the base 2 raised to the power of 3. So the 2 is the base, and the 3 is the power of the exponent. These index laws, hopefully this is just revision for what you did last year, but I'm going to take you through it and prove each one. And so hopefully that will develop your understanding a little bit further and make it easier to remember the index laws if you have a good understanding of where they've come from. So firstly, if I have base A and it's raised to the power of m multiplied by base A to the power of n, because the bases are the same, I simply just add the powers. So let's look at the example here. 2 to the power of 3 multiplied by 2 to the power of 4 becomes 2 to the power of 7. And here's the proof. 2 to the power of 3 can be written as 2 times 2 times 2. And 2 to the power of 4 can be written as 2 times 2 times 2 times 2. So altogether I have 7 lots of 2. So base 2 raised to the power of 7. So it proves that it works. Second index law, similar idea. A to the power of m divided by a to the power of n. Because the bases are the same, I can simply do a subtraction of the powers. So our example again, 2 to the power of 7 divided by 2 to the power of 4 becomes 2 to the power of 3. Let's look at the proof. 2 to the power of 7 can be written as 7 lots of 2's being multiplied together. And 2 to the power of 4 can be written as 4 lots of 2's being multiplied together. The 4 2's at the bottom cancel out 4 at the top, leaving us with 3 2's. I can rewrite that as being 2 to the power of 3. Third index law. This time we've got base A to the power of m in brackets, and all of that is raised to the power of n. So with this third index law, what we're saying here is that we just have a to the power of m times n. Let's look at an example of it. 2 to the power of 4, all raised to the power of 3 becomes 2 to the power of 12. Let's look at the proof. 2 to the power of 4, all raised to the power of 3. So I can think of that as being 2 to the power of 4 multiplied by 2 to the power of 4 being multiplied by 2 to the power of 4. And of course I've got basically 3 lots of 4 lots of 2 being multiplied together. Altogether, you can see that there are 12 2's being multiplied. So that's just 2 to the power of 12. Fourth index law. A to the power of m divided by a to the power of m will become a to the power of m minus m. So that's from the previous index law, which of course will give us a to the power of 0, and that will equal 1. We know that a to the power of m divided by a to the power of m is going to be 1 because it's something divided by itself. And we also know that through this index law, that's a to the power of 0. So the big one here for us guys is that anything raised to the power of 0 is equal to 1. With our fifth index law, I've got a to the power of negative m. I can rewrite that as being 1 over a to the power of positive m. So let's look at an example here. 2 to the power of 4 divided by 2 to the power of 7 becomes 2 to the power of 4 minus 7, which is 2 to the power of negative 3. And what I'm saying is that that can be rewritten as 1 over 2 to the power of positive 3. Let's look at the proof of that. 2 to the power of 4 divided by 2 to the power of 7. So I have 4 lots of 2's at the top, and I have 7 lots of 2's down the bottom. So the 4 2's at the top cancel out 4 at the bottom, leaving us with 1 over 2 to the power of 3. Here we have a multiplied by b, and then all of that is raised to the power of n. What we can do is take out a and have it a to the power of n, being multiplied by b to the power of n. Let's look at the example. 2 times 3, all raised to the power of 4 is 2 to the 4 multiplied by 3 to the 4. And here's the proof. So you can see I've got 4 lots of 2 times 3, and without the brackets. And if I group the 2's together and group the 3's together, you can see I can rewrite it as being 2 to the power of 4 multiplied by 3 to the power of 4. Our seventh index law. So if I have base A and then I take the nth root of it, that's the same as having a to the power of 1 on n. Let's look at this example. So it's the third root of 8. The third root of 8 is a number that when multiplied by itself 3 times over gives us the 8. And what I'm saying is that we can rewrite that third root of 8 as being 8 to the power of 1 on 3. And if we think about that, 8 to the power of 1 on 3 multiplied by 8 to the power of 1 on 3, it's going to equal 8 to the power of 1/3 plus 1/3 plus 1/3, which is 8 to the power of 1, which is 8. And there's some more proof there of that. The more general idea, if I've got a to the power of this fraction m on n, then that's going to equal having a to the power of m and then taking the nth root of it, which is exactly the same as taking base a, then taking the nth root of that, getting the result, and raising it to the power of m. So you can rewrite a to the power of this fraction in either way. And finally, here's a summary of our index laws. It's really essential that you become proficient at using these index laws. You need to be able to recall them easily and apply them. So here in problem 1, we're going to be applying the indexed laws to simplify various expressions. Just to point out that you don't need to show all of the workings that I have, but I've written them down so you can easily understand what I'm thinking in my head. So the first one here for a, what I'm interested in doing is multiplying the numbers together, so 2 times 4. And then I want to group the x's together, so x to the power of 3 and x squared. And the y's, y squared times y. And remember, y is the same thing as y to the power of 1. So 2 times 4 is 8, and then I add the powers for the x, so 3 and 2 gives me the 5, and y to the power of 2 plus 1, so I end up with that as a result. What is it that I'd like to see for sure is that line and then that line. So really at year 11 methods, you want to get yourself to a stage where you can just go, oh yep, 2 times 4, yep, that's 8. X to the power of 3 being multiplied by x squared, so I add the powers together, so that's x to the power of 5. And then y squared times y, that's y to the power of 3. For b, I've got all of this raised to the power of 2 multiplied by x times y to the power of 4. So the big one here with the squared is that everything inside the bracket needs to be raised to the power of 2. So the 2 is squared, and that's the common mistake. X squared is squared, so that becomes x to the power of 2 times 2. And y cubed is squared, so that becomes y to the power of 3 times 2. And I'm multiplying through, tidying things up, and now it's clear to us that I've got no other number. There's a 1 there in front of it, so it's just the 4. And then it's x to the power of 4 multiplied by x to the power of 1, so that gives me x to the power of 5. And y to the power of 6 multiplied by y to the power of 4, so that becomes y to the power of 10. For c, we have that expression divided by this expression, so we set this up as a fraction. And what I'm going to try and do is expand out to begin with, so that's going to be 3 to the power of 5 multiplied by a to the power of 5 multiplied by b to the power of 6 over 9 multiplied by a to the power of 4 times b to the power of 3. So what you should be able to recognise is that that 9 can be written as 3 squared, and that's going to be helpful for us to apply the index laws. And then I've got the rest of it just the same, and so it ends up being 3 to the power of 5 take away 2, which is 3, a to the power of 5 take away 4, which is 1, and b to the power of 6 take away 3, which is b to the power of 3. So 3 cubed is 27. I've just written that as a and b cubed there. Now for d, there's that part written down. Let's expand the brackets to begin with. So it's 3 cubed and p to the power of 3. Then on the top line, I'm going to combine things. So I'm going to have 8 times 27, and that's 216. And p to the power of 6 plus 3, which is 9. M to the power of 2 plus 5, which is 7. Over 6 lots of p to the power of 4 times m. And now simply you do your division. So 216 divided by 6 gives us 36. And you may not have the skills just yet to be able to work that out, but after playing around with a lot more index laws, that should come a bit quicker to you. P to the power of 9 divided by p to the power of 4 becomes p to the power of 5, and m to the power of 7 divided by m to the power of 1 becomes m to the power of 6, so that's the simplified expression. Okay, so problem 2, more of the simplification. So I've got 2 to the power of 3 multiplied by 16 to the power of 2. The idea here is to try and get the bases to be the same and then put it in index form and then look at simplification. So 16 can be rewritten as 2 to the power of 4. Now if all of that is squared, it becomes 2 to the power of 4 times 2, which is 8. And now we've got 2 to the power of 3 multiplied by 2 to the power of 8, which is 2 to the power of 11. B, looking at those numbers, bases 9, 3 and 27, I want to put them all to being the same base. And that base will be 3. So 9 is 3 squared, 3 is just 3 still, 27 is 3 cubed. So I have 3 to the power of 10, 2 times 5, multiplied by 3 to the power of 4 over 3 to the power of 9. Combining the top, I've got 3 to the power of 10 plus 4 over 3 to the power of 9. And so that becomes 3 to the power of 5. And you can leave it in index form or rewrite that as being 243. Okay, C, again, what we have here is 3, 6 and 18. Now when you look at that, there's no particular base that you can think of that we could write 6 in, 18 in and 3. But what you can do is split them up a little bit. So this 18 we can think as being 9 times 2. So the 9 we can rewrite as being 3 squared. The 6 we can think of as being 3 times 2. And that's exactly what I've done. So 3 to the power of 4n, that's fine. This is 18 to the power of n plus 1. So the 18 is 9 times 2, and the 9 can be written as 3 squared. 6 can be rewritten as 3 times 2. So expanding out, as you can see here, and then obviously what I'm interested in is simplifying. So I have at the top line 3 to the power of 4n plus 2n plus 2, which is 6n plus 2, multiplied by 2 to the power of n plus 1 over what you see here. And now what we've got to do is a subtraction. So with the base 3, it's going to be the top power, 6n plus 2, and then we subtract from it the bottom power, 3n minus 2. Notice, guys, that I put that bottom power in brackets, and that's so I don't make a mistake with the negatives. And then with the base 2, I've got 2 to the power of the top power here, minus the bottom power, again in brackets. So looking at that now, I've got 3 to the power of 6n take away 3n, which is 3n. And I've got 2 take away negative 2, which is positive 4. And that's where the mistakes are usually made. And I have 2 to the power of negative 2n plus 3. And just rewriting it so that it starts off with a positive power, and just flipping over that 3 and that negative 2n about. Okay, so just a bit of a summary here about our approach for simplification. Just remember that you're going to use a variety of the index laws. Whenever you've got brackets, do those first. If we've got fractions, then simplify across and then down. So do your top, then your bottom. When we're dividing by fractions, then what you should do is take the second fraction, make it a multiplication and flip it. And then what I want you to also do is express your final answer so that we have positive powers. This is not required for the exams, but when we get closer to exams, we'll perfect that. But for your development, I want you to express it as positive powers. So now what we're going to be doing is taking a look at indicial equations. So the first one here, solve for 5x equaling 125. The whole objective here is to rewrite the left-hand side and the right-hand side so that they are on the same base, and then you'll equate the powers and solve for the variable. So 5x equals 125. I'm going to rewrite the 125 so it's 5 to the power of 3. Now I can equate the powers. So it's just simply x equals 3. We can also do that on our CAS. So I'm sure you've been using the solve function before, but menu, algebra, solve, and then you put in that expression. So it brings up the solve function with open brackets, and then put in whatever you need to. So here's an example of 3 to the power of 5x is greater than 14, and we're solving for x, and that will evaluate it for you. For this particular problem, of course, we would have 5x equals 125, comma x. Now, this stuff here is really, it's handy to know this. So being able to produce these lists here, so I've got 2 to the power of 1 all the way through to 2 to the power of 8, and you can see the numbers there. So the only way to becoming familiar with this particular number pattern is to rewrite it many times. And then I've got base 3s, base 5s, and base 6s. So these come up a little bit. We don't need to be able to work out what 6 to the power of 10 is, but it's not unreasonable to evaluate what 2 to the power of 8 is. You can see I'm just doubling. I'm multiplying by 3. I'm multiplying by 5, multiplying by 6. So this 6 to the power of 3 equaling 216, that comes up a bit as well. So it is handy to know this stuff here. All right, so let's take a look at problem 4. I've got solve 3 to the power of 4 to the x equaling 27 to the power of 2x plus 1. So first of all, I want to get rid of the brackets. So that's 3 to the power of 4x. And I want to rewrite the 27 so it's of the same base on the left-hand side. So I'm going to rewrite the 27 as 3 to the power of 3. Then tidying up the powers. So clearly left-hand side, 3 to the power of 4x equals 3 to the power of 6x plus 3. I can now equate the powers and then solve for x. I get negative 3 on 2. Problem 5, we have an inequality. So I've got 3 to the power of x plus 2 is less than or equal to 81. So that's 3 to the power of x plus 2 is less than or equal to 81. So the 81 can be rewritten as 3 to the power of 4. So remember just there. And now because the powers are the same, the bases are the same, I can look at the powers. So x plus 2 must be less than or equal to 4. Take 2 from both sides, and I get x is less than or equal to 2. Remember that your inequality remains the same, so the sign remains the same, unless you multiply or divide by a negative number. If that happens, then you need to change the direction of the inequality sign. Six. Negative 2 to the power of 4x plus 4x is greater than negative 16. In my first move, I multiply both sides by negative 1. So I need to change the direction of the inequality sign. I rewrite 16 so it's 2 to the power of 4. I equate the powers and I solve for x. Seven. So 4 to the power of 5 is less than negative 64 to the power of 3x minus 4. So let's start with the 64. I'm going to rewrite that so it's 4 to the power of 4. And then I'm going to get rid of the brackets, so I have 4 to the power of 12x minus 16. Notice on the left-hand side I have 4 to the power of 5, but on the right-hand side I have minus 4 to the power of 12x take 16. There is nothing I can do here so that I get the left-hand side base equal to the right-hand side base. So you might think, oh, let's multiply both sides by negative 1. That would make this positive, but that negative. So obviously negative 4 is very different to positive 4. I can't get the bases to be the same, therefore I can't equate the powers, and therefore I can't solve for x. So for this one here, there is no solution. And if you put that into your CAS, you could see that's the case as well. All right, so for problem 8 here, we've got 3 to the power of 5x is greater than 14. Now there's no possible way I can rewrite the left-hand side and the right-hand side so they have the same base. So what I ended up doing is using my CAS. Now if I did that, I would come up with a solution that x is greater than the natural log of 14 over 5 lots of the natural log of 3. Don't be too worried about what the idea of natural log is. I'll explain that to you in a later topic when we do logarithms. So that's the exact answer. And then if I go Control Enter, I'll get an approximate answer of 0.48. Let's look at how we produce that with the CAS. So I want Menu, Algebra, and Solve. And it's base 3 to the power of 5 times x. And that's going to equal 14. And I'm solving for x. All right, so that's the exact answer as you saw in the solutions, and then go Control Enter, and I've got the 0.48, and that's corrected 2 decimal places. 9 here looks really complicated. It's not too bad. I'm going to make use of index laws and also the ability to solve quadratics. So the key to it is that I've got 12 lots of this 3 to the x here. It's similar to 3 to the power of 2x, so base 3 to the power of something. Let's subtract that from both sides, which I've done. And I've rewritten this 3 to the power of 2x, so it's 3 to the power of x all squared. Now what that's achieved is I've basically got some junk squared minus 12 lots of some junk plus 27 equaling 0. So you can see it's like a quadratic. So if I think of 3 to the power of x as being u, I've got u squared minus 12u plus 27 equaling 0, and obviously I could factorize and apply the null factor law and find solutions for u. But why is it that I can rewrite 3 to the power of 2x as 3 to the power of x all squared? Remember, when we're in this format, that what I need to do is just multiply those two numbers together. So the expansion of this would be 3 lots of x times 2, which is 2x. So if I want to put this base 3 and then something other power, I could also rewrite that 3 to the power of 2x as being 3 to the power of 2 or raised to the power of x. But I chose the other way, 3 to the x or raised to the power of 2, because now I've got this lot of junk and this lot of junk being exactly the same. So some junk squared minus 12 lots of that same junk plus 27 is equal to 0. I now make the substitution that u is equal to 3 to the power of x. So I've got u squared minus 12u plus 27. I factorize, so I've got u minus 3 multiplied by u minus 9 equaling 0. So obviously u is equal to 3 or u is equal to 9. Now I sub back in the fact that u is equal to 3 to the power of x, so I've got 3 to the power of x and 3 to the power of x. I rewrite the 9 so that it is of base 3. And because I've got bases the same on the left-hand side and the right-hand side and equate the powers, so x is equal to 1 and x is equal to 2. So the key to it is to recognize that I've got this 3 to the power of x. It's similar to what I started with here. I can manipulate that so it's 3 to the x all squared, and that's the same as this, and therefore I can make the substitution. These are very specific, so when you do see problems like this, the key to it is to look at, oh yeah, I've got this number and then I've got this base to something with the variable x. Obviously, I need to be able to manipulate some other term in here so that it looks similar to this, and obviously that's going to involve that 3 to the 2x, and that will produce a quadratic for us. So a bit of practice on that one, and it won't be as daunting as you can see just here. So whenever we're dealing with indicial equations, remember 2, 3, 5, and occasionally 6 pop up. If the bases are the same, we equate the powers. A negative number can't be expressed in index form. For example, negative 4 can't be rewritten as 2 to the power of something. And make use of the null factor law. And you saw that in that last example there.